Hello student, to the foundation of classical electrodynamics course. So, we have already completed our theory part. So, in last couple of lecture we will going to discuss about few problems. So, today under tutorial 2 we going to discuss few problem related to electrostatics. So, today we have class number 71. Okay, so let us directly jump to the problem. So, the problem 1. So, the problem 1 states that suppose the electron cloud around the nucleus of charge plus E in an atom can be represented by this following charge distribution. So, the charge density is represented in this way. Minus of pi r cube and then r 0 cube and then e to the power of minus 2 r by r naught, where r 0 is a Bohr radius constant, r 0 is Bohr radius. So, the question is calculate the total charge. So, the charge distribution is given, we need to calculate the total charge, that is the problem. So, let us directly solve it, the solution. So, since the charge distribution is given and this charge distribution is a function of r, so we can take a small section of this charge distribution, because so this is r and from here to here it is r plus dr. Now, total charge q, I can write it as the integration of the charge density over the volume, and r can this volume can go from 0 to infinity in principle. So, here my dV is how much? dV is 4 pi r square dr, and then my q is 0 to infinity rho r, and then this 4 pi r square dr. So, if I now if we put the value of the rho, which is this one, which is given, so minus E divided by pi r cube. So, this quantity I can take it outside. So, I simply have minus E divided by pi r 0 cube, and then we have 4 pi, and then we have the integration 0 to infinity e to the power of minus 2 r by r naught, and then r square dr. Okay, that should be our integration. Now, this integration is a special kind of integration. So, we will going to discuss that. That is why I put this problem here. So, let r 2r rather divided by r 0 as a new variable, say x, so that r square is simply r 0 square divided by 4 and then x square. So, if that is the case, then we are just changing the variable. We can write my dx as 2 divided by r naught dr. Okay, I am going to replace this dr here, and then my integration in terms of, so few terms are going to cancel here. Let me cancel this. For example, this pi and pi will going to cancel, and we eventually have my integral q is equal to minus of 4 e divided by r 0 cube, and then integration 0 to infinity. Then we have e to the power of minus x, because e to the power we have minus 2 r divided by r 0. So, that quantity I have minus x, and then r square I just replace here the value of r square, which is r 0 square divided by 4 x square, and dr I replace, which is again r 0 divided by 2 and then dx. So, this integral, so let everything outside. So, we have minus of 4 e, and we have here r square, here r. So, this quantity should cancel out, and these 4 also going to cancel out. So, we have simply e divided by 2 at the outside. We should have minus of e divided by 2 integration 0 to infinity e to the power minus x, then we have x square dx. So, this is a very special kind of integral called the gamma function. So, let me write it here how the gamma function works. So, this is called the gamma function. What is gamma function? The gamma function normally defined at gamma n, and it is defined like 0 to infinity e to the power of minus of x, x to the power n minus 1 dx, that is called gamma n. Now, there are some properties. For example, gamma of 1, that value should be equal to 1. In general, we have gamma n plus 1 is equal to n multiplication by the gamma n, and also one useful value is gamma half, that value is equal to root over of pi, very important quantity. In many cases in physics we encounter this value gamma half, but here if I consider with these expressions that this quantity e to the power minus x, x square dx 0 to infinity, if I tally with this, then the value of the n here is 3. So, eventually my q should be, my q is simply minus of e divided by 2, and then we have gamma 3. Now, gamma 3 is minus e divided by 2, gamma 3 I can write it as gamma 2 plus 1. So, that thing is minus of e by 2 multiplied by 2 and gamma 1, and gamma 1 is 1. So, eventually we have this value is minus e. So, the total charge should be minus e, and that is expected, because if you look carefully the problem, it says that suppose the electron cloud around the nucleus of the charge plus e. So, charge of the nucleus is given as plus e. So, the total charge distribution for the electron cloud has to be minus e to neutralize that atom, and we are having the same result here. So, that is my problem 1. So, let us go to problem 2. Problem 2. So, the problem 2 is this. Find rho when potential phi is given as phi, which is the potential, electrostatic potential is a function of space x y z, is given as a minus b x square plus y square minus c log of x square plus y square, where a, b, c are constant. So, the question is simple, that the potential is given and we need to find out the charge density. So, here we are going to use this solution. So, we will going to use the expression that divergence of E, we know that is rho by epsilon naught, and then we know that my E is minus of this quantity. So, if I put there, then we have a Poisson equation, and which suggests that we have phi is equal to minus of rho by epsilon 0. So, eventually we need to find out this, the explicit form of phi is given. I just need to find out what is the value when we apply this Laplacian over this phi, that is all. So, So, this operator is simply d2x plus d2y plus d2z in shorthand notation. This is the way we represent the operator here, and that should be operated on the function phi. So, now if I go back to the function, it is a minus b x square. So, I just do the operation here, and first we have minus 2b, then we have minus c and del x. It will going to operate over 2x divided by x square plus y square, because this is the way it is here. So, I need to make a derivative with respect to x. So, here for log we will have this, and then for y we have minus of 2b and then minus of c again del y, and then again we have 2y of x square plus y square, and that quantity is equal to minus of rho by epsilon naught. Now, from here I can calculate rho, because the left hand side, and if I execute the left hand side, then the left hand side will be something like this. So, let me complete that. So, we have minus of 4b, and then if I take c common, c, then we have something like 4 x square plus y square minus 4 x square plus y square. It seems they will cancel out, divided by x square plus y square whole square of that, and the right hand side we have minus of rho by epsilon naught. So, this quantity associated with c will going to cancel out. You can check it. I mean, I am not doing the explicit calculation here. So, then my rho simply becomes 4b epsilon naught. That should be our result. So, what is the strategy of this problem? When you are asked to find out rho by giving phi in explicit way, you just need to use the Laplacian equation. That is the strategy we are using. We use the Laplacian equation, find out the left hand side, and that should be the value of the rho. Okay. Then after that, maybe we will go to another problem, and the problem is again related to the charge density. So, this is problem 3. So, the problem is, suppose a charge q is distributed within a sphere within a sphere of radius r in such a way in such a way that the charge density at a certain distance is given as this r. Rho is not distributed uniformly. So, the variation of the rho is given. It is like the problem we had in the as a problem 1. So, the Q is distributed in such a way that the charge density is not uniform and it is distributed in this way. From the origin to certain r, this is this, and beyond that it is 0 when r is greater than r. Now, the charge distribution is given. The question that is asked is 1. First thing we need to find out, find k, find the value of k in terms of total charge. So, that we will see. Second part of the second question is find E electric field at some point r where r is less than r. Third point is find E max. So, there should be a maximum field, then find out where the field will go to maximum for r less than r, again this condition. So, here we find ER and now we need to find out what is the maximum r, and that is these are the 3 problems we need to do. So, the strategy is straightforward. The solution for the problem 1 is this: Q should be equal to 0 to r and rho r dV. So, that we know, and rho is given here, the charge density is given here. So, we will going to exploit that expression to find out what is the total charge. So, it is 0 to r and then it is k r minus r, and since rho is only depends on r. So, the dV I should write simply 4 pi r square dr, exactly like the first problem. This is r dr. Okay. So, if I integrate that, my Q should be simply 4 pi k, and then the integration in this limit is simply r, and then this is okay. Let me do the integration first. R q divided by 3 minus r to the power 4 divided by 4 from 0 to r, sorry 0 to big R, that is the limit, and that value is simply, if I put that value r, and this is, so it should be r divided r cubed r to the power 4 divided by 3. So, okay, so it should be 4 pi k, and that value is r to the power 4 divided by 12, and this 4 will going to cut with the 12 and we will have 3 here. So, my Q, what I find is simply pi k and then r to the power 4 divided by 3. So, from here I can find out what is the value of the k, that is the problem 1. My k should be, in terms of total charge, my k should be 3 q and then divided by pi r to the power 4. That should be my first answer. What about the second one? What is the electric field? So, I will go to use the Gauss's law here simply. Problem 2 is I will going to use line integral total surface integral ds is equal to q enclosed divided by epsilon 0, okay, because I need to find out the field for this spherical distribution where the rho is changing with a function of r. So, I can take a Gaussian surface here and calculate the electric field. That is the simple strategy. So, at r from here to here, I can have, sorry, this should be smaller because this is bigger is the radius. So, it should be smaller. So, E then 4 pi r square, that should be the charge enclosed. So, charge enclosed I need to calculate. So, it should be rho at that point over the dV 0 to r. So, that quantity 1 divided by epsilon naught and rho is given. So, it is integration 0 to r k r minus r, that is the way it is changing, and dV again I should have 4 pi r square dr. So, if I do this integration, then okay, let me write the left hand side, it will be E 4 pi then r square, that is equal to 4 pi k divided by epsilon naught and the integration 0 to r. The thing I need to do is r square minus r cube, that I need to do, that I need to integrate. So, that quantity I simply find out as 4 pi k divided by epsilon naught, and this is r then r cube divided by 3 minus r to the power 4 divided by 4, that is all. So, my E at any point r should be, the 4 pi will cancel out, it should be k divided by epsilon naught and then we have r divided by 3 minus r square divided by 4. So, this is my E, and the third point is for maximum E, what we do, we will calculate this quantity. So, this quantity give us a value of r at which the E should be maximum, and if I calculate, it is easy to find that r maximum where the E is max is simply 2/3 of r. So, that means if I put r as 2/3 of r here, then I am going to get the maximum E. So, maximum E max should be simply E at where at the position of R max. So, that is k divided by epsilon naught, and then we have the value here. So, R divided by 3. So, I simply have R divided by 3, then 2/3 R, and then minus of 1 by 4, then 2/3 square, and then R square. So, eventually I have E max. If you just calculate that, you will going to get this result in terms of total charge, because k is already there, we know what is the value of the k. So, if I put the value of the k, it should be q divided by 3 pi epsilon 0 R square. I am not doing the rest of the part because this is a simple algebra. So, I believe you can figure it out that what is the value of the E max when you put this. Okay. Now, let us go to problem 4. This interesting problem. The problem 4 is, let me draw that, then you are going to understand what is the problem. I have a half hemisphere hemispherical bowl like this of radius r. So, we have a radius here and that value is r. So, we have 2 points here. So, this is the pole. Okay. So, I have 1 point and this is another point. So, the surface charge density here is sigma, is the surface charge density, and the question is the potential difference between this north pole, this is north pole, and the center, this is center. So, the problem is delta phi. What is delta phi? The potential difference between the center minus the north pole, say phi p. So, this is potential here is C, and here the potential is P. So, what is the potential difference when there is a surface charge distribution is there and sigma is a surface charge distribution. So, let us find out what is phi c first. Phi c is phi 0, or that is the reference, say 1 by 4 pi epsilon naught, and according to the formula we simply have this, because this is over the surface, all the points are from same distance. So, this central point is the distance is same. So, r is same. So, let me take okay, I will do that later. So, that value simply I have 1 by 4 pi epsilon 0 r, then sigma, and integration of the ds is simply 4 pi r square, and that is divided by 2, half of the sphere. So, this quantity I simply have sigma r divided by 2 epsilon 0. Now, the interesting part is the next one, how to find out the potential at north pole. So, in order to do that, let me draw a section here, a small section like this, and from here to here, suppose this distance is r. Now, this r is changing every time. So, that is the trick we are having here. So, we need to take care of that issue. So, the phi pole should be 1 divided by 4 pi epsilon naught, and then the charge over the small surface area, which is defined by this ring here, divided by r, right. Now, here ds is simply 2 pi multiplied by r sin theta and then r d theta, because this angle, if it is theta, then if I calculate this surface area, then this surface area should be this one, okay, r sin theta, because I am taking from here to here this distance, and then dr, and then r d theta is this strip, this portion of the strip. So, it should be the surface area of this small section. What is r? So, there is a relation. So, because if I calculate r, small r, in terms of this is r and this is also r, from here to here this is also r, and the angle between these two is theta. So, then I can simply have my r square as 2 of r square minus 2 r square cos theta. It is simply r square plus r square minus 2 r into r cos theta. The angle between the two vector is theta and the magnitude of two vector is r. So, the other arm, if I want to find out, I simply use the vector law, and this is the way one can find. So, this is my r square. So, I am going to put this here and I will get the result. So, phi p then simply equal to sigma divided by 4 pi epsilon naught 0 to pi by 2, and then we have 2 pi r square sin theta d theta. I am just writing ds here, and below we have r. So, we have 2 r square rather multiplied by 1 minus cos theta whole to the power of half, whole to the power of half. So, simplifying this, we have sigma r divided by 2 root 2 epsilon 0 to pi by 2, and then if we have simply sin theta d theta divided by root over of 1 minus cos theta. Okay. So, that thing is, because I can write sin theta as a d of cos theta, and then the rest of the thing I calculate. So, it should be simply gamma r divided by 2 root 2 epsilon naught, then we have 2 root over of 1 minus cos theta with the limit 0 to pi by 2, and that value is simply sigma r divided by epsilon naught and root over of 2. So, then my delta phi, which was there in the problem, is simply rho p minus phi p minus phi 0 that is equal to sigma r divided by epsilon naught 1 divided by root over 2 minus half. That should be our result. You can simplify this result more. So, it is sigma r divided by epsilon naught, and then how much? It is root over of 2 minus 1. If I multiply 2 here, it should be 1, it should be root over of 2. So, I need to have 2 here. Yeah, it should be something like this. So, that is the difference between the potential for this system. The trick here is to calculate the potential at the north pole, where the distance is changing continuously. Okay, now go to the next problem. The next problem is something like this. Problem 5, and say the problem is, consider a disk of radius, consider a disk of radius r of charge density the charge density of the system is of the disk is given. Now, the charge density here is a function of r and theta, which is say sigma 0 r cos theta. This is the way the charge density is changing. So, the problem is find monopole and dipole moment of this system. So, solution, what the problem says is that like this. I have a disk here, this is the center of the disk, and from here to here, suppose I am having a coordinate system. So, this is x and this is y. So, at this point, this is say r and theta, the value of at this point, the value of the potential at this point is defined by the value of the surface charge density is given as this is a function of r and theta. So, r is changing, also sigma will going to change, theta change, sigma is also change. So, I need to take care of that issue. So, monopole moment means total charge. So, total charge we know how to calculate. For the surface charge density, it is sigma r theta over the entire surface ds. So, it is sigma 0, and then I should have r cos theta. How it is distributed? R cos theta. So, it should be r of cos theta, and ds is the surface element in polar coordinates. It is r dr d theta, and that is all. So, if I calculate sigma, then it will be 0 to r for r square dr, one integral, and another is 0 to 2 pi for cos theta d theta. So, the second integral will going to vanish, because this has to be 0. So, if this is 0, then we simply have q is equal to 0. So, monopole moment will not be there. So, the total charge distribution is such a way that the total charge, the charge distribution is here in such a way that total charge is 0. So, the positive and negative charge they are equal. So, there is no neat total charge. What about the dipole moment? For dipole moment P, we know our expression, it should be r prime sigma divided at r prime and ds prime. So, this is by definition the dipole moment. R prime here is the location and the point, and this is r prime cos theta x plus r prime sin theta y. So, P then simply integral of this. So, I have r prime cos theta x unit vector plus r prime sin theta y unit vector, and then I have the sigma r prime cos theta prime, that is the surface charge density, and then we have the surface element which is r prime dr prime d theta prime. Now, if I calculate for x and separately for x and y component, the x component, if I calculate sigma 0 I can take outside, it should be 0 to r and then r prime cube dr prime, and then we have 0 to 2 pi and we have cos a square theta prime d theta prime, and y component will be y sigma 0 integration 0 to r, again we have r prime cube dr prime, but here we have 0 to 2 pi and then we have sin theta prime cos theta prime and then d theta prime. So, we can see that this quantity has to be should be 0, and eventually what I am getting in on the x component. So, the x sigma 0, it should be r to the power 4 divided by 4, and then this quantity is half of 2 pi and y component will be 0. If you do the calculation, you will find that. So, eventually my P should be x sigma 0 r to the power 4 divided by 4 multiplied by pi. So, this is the way we can calculate when this is a distribution of the charge. You can calculate the monopole and dipole moment by exploiting the basic expression, and we are going to get this. Okay, after that we will just go to the final problem. So, problem 6, and the problem 6 is saying that we have a dielectric. So, I am not writing the problem, I am just so hope you will going to understand that, because I am saving some time. So, we have a dielectric block here with the length L both the sides, and the P, the polarization of this dielectric is not uniform. This is a function of R like this. This is the polarization. Polarization is a function of R. Now, the question is find bound surface charge density and bound volume charge density. So, let us solve this problem. So, we have a dielectric cube where the polarization is a function of R like this, and now we need to calculate the surface charge bound charge density and volume bound charge density, and also we need to show that if I add these two charge, then it should vanish, because there should not be any net charge. Okay. So, we know how to calculate the surface charge density if the polarization is given, and so what is the, okay, let me write down the polarization here first. Polarization is lambda r, which is lambda xi plus yj plus zk, and the polarization for any surface is Pn, that is where we calculate at the surface, on top of the surface. So, here for one surface I can simply calculate the surface, say at x equal to L by 2. If I consider my coordinate at the center here, so this is the coordinate at the center of this block, then at x equal to 2 it is dot I calculated at x equal to L by 2. So, this quantity is simply lambda x divided calculated as x L by 2. So, it is simply lambda L by 2. This is the surface. Now, there should be, I mean, the total, if I want to calculate, this is the charge density, the total charge bound charge, surface bound charge for surface, if I want to calculate at x equal to L by 2, then I should simply write sigma b over ds for one surface. Say this is one surface of this block, sigma b is known. If I want to calculate what is the total charge, I need to integrate it over the surface. So, that quantity that is at x equal to L by 2 point. So, that quantity if I calculate for surface, it is minus L by 2 to L by 2, minus L by 2 to L by 2. Sigma b I already calculated, this is lambda L divided by 2, ds is dy dz, because this is x surface. So, dx is dy dz. So, that quantity is simply lambda L divided by 2 and L square. So, it should be lambda divided by 2 L cube. Okay. That is for one surface. How many surfaces are there? That 6 surfaces are there. So, the total bound surface charge Q Bs for total surface bound charge should be 6 multiplication of that quantity, because there are 6 surface, all the surface you will going to get the same value. So, we will get 3 lambda L cube. What about the volume bound charge? So, we know the volume bound charge rho b is minus of divergence of this quantity p, which is simply minus of 3 lambda, right. So, the total bound charge then how much? Q total bound charge for volume should be integration, volume integration rho b dV. Now, rho b is minus of 3 lambda and then integration of dV over this cube. The volume of the cube is L cube. So, it should be minus of 3 lambda L cube. Now, interestingly, if I try to find out what is the total bound charge, then it will be the combination of the bound charge for the surface and the bound charge for the volume. So, this quantity is plus 3 lambda L cube, but this quantity is minus 3 lambda L cube. So, they are going to cancel out and we are going to get 0, which is expected. There should not be any bound charge here. Okay, so we are now running out of time. So, with that note, I would like to conclude today's class. So, today we cover almost all kind of problems with the limited time. So, I believe you are going to practice different problem from the books and you can able to do this problem by your own. So, we will have another class and that should be our last class, where we discuss some problem related to magnetostatics. So, with that note, I will conclude here. Thank you very much for your attention. See you in the next class.